Patty's Calculus Videos, written and performed by me, Patty Leitner.
Part 4. Integrals. Section 5.1. Areas and Riemann sums.
Lesson 1. The right and left-hand rules. Part 1. In this section, 5.1, we are going to be talking about areas. And I know that probably seems completely unrelated to what we've just been doing, which is finding antiderivatives and finding indefinite integrals. So I want to remind you that although this seems completely unrelated to what we did in that section that we called 4.9/ I think we said 5.4, which was antiderivatives and indefinite integrals, these two will seem as if they are completely unrelated, but when we get to section 5.3, we will see that there is a wonderful theorem. I'll just put wonderful, magical theorem that connects these two ideas together. So just suspend your disbelief for a section, listen to all this stuff on areas, and when we get to the next section, 5.3, I promise to show you that magical, amazing theorem that connects these two ideas, antiderivatives and areas, which probably seem as if they have nothing to do with each other. Okay, so let's focus on areas for now. I'm going to start with a question. What kinds of shapes do you know how to find the area of coming into this course? Well, all through algebra and even pre-calculus, there are really only a few shapes that you have an idea of how to find the area of. For example, a rectangle. Okay, that I know how to find the area of. If it has length L and width W, the area I know is equal to the length times the width. So that I know how to find the area of. You probably know the formula for the area of a triangle, which is really proved based on the area of a rectangle. If it has some base B and some height H, then the area of a triangle, so this is another shape we know, is just 1/2 the base times the height. And someone may have proved this to you based on the formula for the area of a rectangle. And you probably know the formula for the area of a circle of radius r. So that's probably the other basic one that everybody knows. And the area of a circle is pi times its radius squared. And of course you could find areas of shapes that are compound shapes that are made up of rectangles and circles and triangles and things like that. But there's not very many shapes that we know how to find the area of, and I'm betting that although this triangle formula may have been proved to you based on the rectangle formula, I bet nobody's even proved why the area of a circle is pi r squared to you. And that's something that actually can be proved using integral calculus, and it's usually discussed in second semester calculus. So very few things that we know how to find the area of. Well, it turns out by the time we get through that section 5.3 that is coming up next, you will go from knowing how to find the area of 3 shapes to knowing how to find the area of an infinite number of different shapes. So you're going to expand by a factor of infinity the number of things you know how to find the area of. So how cool is that? That's really fantastic. Okay. So I wrote down here that in this chapter we'll learn to easily find areas that look like this, where we have a nice continuous function. For the time being, we're going to be looking at functions that lie above or on the x-axis, not ones that go below, but we'll discuss those as well in the next section. So we're going to be finding the area underneath a curve. It could be really a very complicated, wiggly curve, as long as it's continuous on the interval from A to B. And another question that you might kind of keep in the back of your mind is, what do we even mean by the area of this region? When I shade this in green and say how much green area is there in this region that I called S, well, what do I even mean by that? We sort of have an intuitive idea. We think, oh, it's kind of how much, I don't know, space. It's very hard to put into words when you start to try to think, how do I explain to someone who's never heard of the concept of area what I mean by this green area that's shaded in here? So that's another question that we're actually going to answer. What do we even mean when we say the area, this green area that's shaded here? And just to let you know, we are going to assume that we know this much, that we've defined the area of a rectangle as its length times its width. For example, if you have a piece of carpet that is 6 feet by 2 feet, we know that the area is 6 times 2, or 12 square feet. So we're going to assume this much, that we've defined what we mean by the area of a rectangle as its length times its width. And it turns out that we can define the green area that's shaded here purely based on the formula for the areas of rectangles. So we're going to see how to do that as we proceed in this section. Okay, let's go ahead and look at the next page and look at a specific example, and we'll come back to this specific example a few different times. Suppose I ask you to find the area under the curve y equal root x, and remember this is the top half of a parabola that opens to the right, and we're going to find that area from a starting value of x equals 0 up until I get to x equal 8. So I'm going from x equals 0 to x equal 8, and I want to find the exact value of this green shaded area. Well, we have no formula for it. It kind of looks like a triangle, so I suppose that you could use the formula for the area of a triangle to estimate that area, but it isn't a triangle. It's the top half of a parabola. So at this point in time, we have no way to get the exact green area that I have shaded in there. So since we can't find the exact area, let's estimate it, and there are different ways to estimate it, but because I only want to use the definition of the area of a rectangle, length times width, I'm going to eventually use rectangles to estimate this green area. So how do I do that? Okay, first of all, I'm going to go ahead and break this up, this green area up, into 4 strips that all have equal width. Okay. So I want to break the interval from 0 to 8 into 4 equal length strips. Usually we call the width of each strip delta x because it's a change in the x value. So that's the width of each strip. And if I'm going from 0 to 8, I'm taking an interval that is 8 units long, and I'm dividing it into 4 equal pieces. So each strip is going to have a width of 2. So let's go ahead and mark that off. I'm starting at 0, and I'm going to have one strip that ends at 2. I'm going to have another strip that ends 2 units more to the right, so that'll end at 4. A third one that ends at 6, and my last strip is going to end at 8. And you notice that these are 4 equal length strips. All right, and the width of each of those strips is what we call delta x, and they're all of equal width, so they're all a width of 2. If you want to, you can call this strip S1, this strip S2, this strip S3, and this strip S4, so 4 different equal width strips. Now let's go to the next page and see what we do with those strips. Okay, so how are we going to use rectangles to approximate the area of these 4 strips? Well, we're going to do it as follows. We're going to approximate the area of each of these strips with a rectangle where the width of of the rectangle is going to be the same as the width of the strip. And remember, if we look at, for example, this strip, we already know what its width is. The width we call delta x, and it's 2 units long. And that's actually true for all 4 strips. And how about the height of the rectangle that we want? The height is going to be the height under this black curve at the right-hand endpoint of that strip. Okay, so what do I mean by that? I'm going to concentrate on this first strip. Its width is 2, and I'm going to create a rectangle that has the same height as the height under this curve at the right-hand endpoint of that strip. We sometimes call this interval here a subinterval. It's a subinterval of the interval from 0 to 8. So we have all these x values from 0 to 2, and I choose the x value that's at the right-hand endpoint of that strip, of that subinterval. And there's a certain height under the curve, that's this green height that's right here. That's going to be the height of my rectangle. So I'm going to create a rectangle that's that high, and that has the same width as the strip. And whatever the area of this purple rectangle is, that's what I'm going to use to approximate the area under the curve for that particular strip. Now, this doesn't look like it's going to be a very good approximation. I can see it's going to be way too big because there's a lot of rectangle hanging over the curve, but we'll worry about the fact that it's not a good approximation later. Okay, so I do need to kind of figure out what this height is. And this height that I have underneath the curve is really just the function evaluated at this x value. It's really f of 2, where this black curve is my curve y equal f of x. And why is it f of 2? Well, if I plug 2 into this function, go over to the x-axis, that's what the output would be, f of 2. And of course, this distance on the y-axis is exactly the same as this green height underneath the curve. So if I look at my first rectangle, I'm going to be finding the area of my first rectangle. I want to do the height times the width. And the width we said over here is just equal to 2, so I knew that. And the height is just the value of my function at the right-hand endpoint. It'll be f evaluated at this x value of 2. And what is that equal to? Well, remember, we know what function we have. It's y equal root x, or I could write that as f of x equals root x. So the height is just going to be f of 2 would just be square root of 2. So the height is square root of 2, and I multiply by my width of 2. So the area of the first rectangle, we would usually write that as 2 root 2. And that's my approximation for the area underneath the curve, the area of that first strip. So that's the area of my first approximating rectangle. Now we move to the next strip. And if I look at the next strip, it goes from an x value of 2 to 4. We can see that the width is exactly the same as the width of the last strip. So the width is still equal to 2. And I want to figure out the height of that rectangle by going to the right-hand endpoint of that strip, of that subinterval, and that would be the x value of 4. So I'm going to use this green height underneath the curve as the height of my second approximating rectangle. So I make a rectangle that's that high. And so I'll get a rectangle that looks something like this. Trying not to cover up what I did before. And that will be my second approximating rectangle. I can again see that it looks like this approximation is not going to be great. It might be a little bit better than this one because it looks like the amount that it hangs over the curve is a little bit better. Well, what is this second height here? It's the same as the value of the function at this x value, the right-hand endpoint, which is 4. So the height of this second rectangle is just f evaluated at 4. So let me put that in here. For the second rectangle, I just do f evaluated at the right-hand endpoint of that second strip. And since my function is root x, I'm just going to get square root of 4 times 2. And actually that's a perfect square, so 2 times 2 I get 4. that's the area of my second approximating rectangle. And I just repeat this for the last two strips. So for the next strip, I again have a width of 2, and I choose the right-hand endpoint to create the height of my rectangle. So my rectangle is going to have the same height as this green line underneath my curve. And I get a purple rectangle that looks like this. This one actually looks like it's going to be a little better as an approximation because it does not hang over my strip area very much. And how do I figure out the height of that third rectangle? Well, it's the same as the height underneath the curve at an x value of 6, so that would be f evaluated at 6. So my third rectangle would be f of 6 times its width of 2. F of x is square root of x, so that would be square root of 6 times 2, or we'd probably write that as 2 root 6. And I do the same thing for the last rectangle. Its width again is a width of 2. And I want to create a rectangle that's as high as the height underneath the curve at the right-hand endpoint of that strip. And when I concentrate on the x values from 6 to 8, that would be the x value of 8. So I go ahead and create my rectangle to have this green height, and I would end up with a rectangle that looks like this. And that will be my approximating rectangle. Whatever the area of that rectangle is my approximation for the area under the curve. Again, it's off a little bit, but that's an approximation. What is the height of this rectangle? It's just the height under the curve at an x value of 8, so it's just f evaluated at 8. So the height of my fourth rectangle is f evaluated at 8 times its width of 2, and that would be square root of 8 times 2. Square root of 8 is 2 root 2. I multiply by another 2, and I get 4 root 2. So these are the areas of my 4 purple rectangles. I'm going to add them all up to get an approximation for that total green area that we had on the last page. Let me just put that back up here for a moment. I'll put these side by side. We were trying to approximate this green area under the curve from 0 all the way to 8, and we're going to use the sum of the areas of these purple rectangles as our approximation for this green area. So let's go ahead and add all of those together, and that's what we call R sub 4. R, we use the letter R because we are using the right hand endpoints on each strip. That's what we said up here. We're using the right hand endpoint on each strip in order to approximate the area. So R4 is just going to be the sum of these things. So it will be 2 root 2 plus 4 plus 2 root 6 plus 2 root 8, which simplifies to 4 root 2. That is on our approximation for the original green area under the curve all the way from 0 to 8. And I plugged that into a calculator, and I'm looking at my notes over here. When I plugged this into a calculator, I got 17.3842686 approximately. So that's what I'm getting as being my approximation for the true green area that was under that curve. So that's my approximation for this green area. Now, let me ask you a question. Is this estimate too big or is it too small? So when I add up these purple areas, are they going to be more than the green area or less than the green area? And I think it's clear that for this particular function, since it's increasing this way, they're going to be too big. So in our particular example, I'll say in this example, for this function, it's too big. If we had another function that was decreasing as we move to the right, you would actually get a sum that the rectangles would be below the curve, and you'd get a sum that's too small. So for this particular one, though, it looks like we get a sum that is too large. Okay, great. What if instead of using these right-hand endpoints, I had decided to use the left-hand endpoint to create the height of each rectangle? So that's what we're going to ask on the next page. What if we made the height of each rectangle the left-hand endpoint on that strip instead of the right-hand endpoint? Well, we can certainly do that. Let's look at our first strip. We can see that the width of that strip is still 2. Actually, the width of all of our strips is still equal to 2 units. But now when I create my rectangle, instead of going over to the 2, the right-hand endpoint of that first strip, I'm going to use the left-hand endpoint. Well, for this function, where is the left-hand endpoint? How high is it? It's 0 units high. It's right on the x-axis. So for my very first rectangle, I would create a rectangle that's 0 units high and 2 units long. It would be like it's degenerated into just a line segment instead of a rectangle. If I wanted the area of this line segment, well, it would be its height, but its height is really square root of 0, which is 0. And its width is 2 units long. So the area of that first rectangle is really going to be an area of just 0, because the height is square root of 0, which is 0, and I multiply by the width, which is 2. Okay, let's go to the next strip. It'll look a little more interesting. I look at the next strip. I'm considering x values from 2 to 4, and I want to pick the height of my rectangle to be the same as the height under the curve at the left-hand endpoint. So that would be at x equal 2, and this height right here, this green height, would be what I want to use for the height of my approximating rectangle. So I make a rectangle that's that high, and I would get a rectangle that looks something like this. What's the area of that approximating rectangle? Well, I can see that the width is 2 and the height is this height right here. It's the height underneath the curve at the left-hand endpoint, so that would be f of 2. And f of x is still square root of x, so f of 2 would be square root of 2. So my second rectangle would have a height of f of 2 times the width of 2, or square root of 2 times 2. Or if I want to simplify that, 2 root 2. And we continue to do this for the third strip. I want to use the height at the left-hand endpoint. That would be this green height right here. And so I create a rectangle that's that high. That will be my third approximating rectangle. And so we know the width of that one is also 2. How high is it? Well, the height I get by looking at this height right here. That would be my f evaluated at the left-hand endpoint, which is 4. So I would have a height of f of 4, that's square root of 4 times 2. And I go to my last approximating rectangle. Its width is going to be 2 again, and the height I'm going to make the same as the height at the left-hand endpoint. That would be at the x value of 6. So the height is going to be the same as this green height under the curve at the x value 6, and I would get an approximating rectangle that looks like this. And we ask, well, how high is that? It's just f evaluated at that x value. It's f of 6, and f of 6 for this particular function is root 6. So my last one would be root 6 times 2. So I actually get root 0 times 2, root 2 times 2, root 4 times 2, and root 6 times 2. I add all of those up. I guess I could simplify this. This is 2 times 2 is 4, and this would just be 2 root 6. I add up those 4 rectangles' areas, and I get a certain value. Let me see what my notes say I get. I get approximately 11.72740661. So that's my approximation for that green area underneath the curve that we were originally trying to approximate. So this number right here is my approximation for this green area. Well, is this estimate too big or too small? For this particular example, which is a function that's always increasing on the interval that I'm looking at from 0 to 8, it looks like when I add this area, which is the area of a line segment is just 0, plus this area, plus this area, plus this area, I can see clearly that the purple rectangles are going to add up to an area. I can see clearly that the purple rectangles areas are going to add up to something that is smaller than the green area underneath the curve. So this estimate of 11.72 is something that is too small. Well, a question we might want to ask is, how could we get a more accurate estimate of this true green area underneath the curve? And there's more than one answer to this. One thing you might think of immediately, I'll call it answer number 1, is that we could take this estimate that was too small and add it onto our estimate that we knew was too large from using the right-hand endpoints for the heights of our rectangles. So if we go back over here, here was our estimate that we knew was too big, and here's our estimate that we know is too small. What if we average those together? We ought to get something that's sort of in between and would be closer to that true green area of the curve. So let's go ahead and do that. Let's find the average of the sum of the right-hand endpoint rectangles and the left-hand endpoint rectangles, and the average would just be equal to R sub 4 plus L sub 4. Oh, by the way, the reason we use this subscript of 4 is that we're using 4 rectangles, 4 subdivisions, or 4 strips in each case. We did the same thing when we used the right-hand endpoints as the place where we evaluated our heights. We had 4 different rectangles, and so it was R sub 4. So R sub 4 plus L sub 4, and divide that whole thing by 2, and the value that I got was 14.55583331. And even though we don't know what the true area, the true green area under the curve is, we're confident that this would be something that would be closer than either L4 or R4. So that would be one way to improve our estimate. Well, there's another way to improve our estimate, so let's think about that.